All right, we've talked a bit about structural testing coming from code, but another thing we need to talk about is something called model-based testing. This is very useful when you don't have your source code yet, and maybe you have your specification and you want to come up with a way to test your specification, your specification came up, or it may be a case where you have a business process and you need to do some type of testing of that process as well. Now, this may seem like it's out of scope of what we're doing for this class, with being that we're trying to focus on software engineering, but it really can become very important, especially in a lot of situations, because what happens from the administrative side will affect what you do in your job. So in certain times it is actually very useful to go ahead and look at a model, but even beyond that, a lot of times you'll have a specification, but you haven't been able to code anything up yet, so you still need to be able to test the specification. Now, that doesn't come up too often in practice because most of the time people are just trying to get something out, but if you are doing a full-blown project on a very large scale or a very life-saving project, then you're going to be wanting to test your specification as thoroughly as possible. And that's what model-based testing is you come up with some type of model and you come around and you test it. And we're going to talk about a little bit about model-based testing and how do we derive test cases for the model. All right, I just went over this. Okay, fortunately these slides are a little on the bad side, so we're going to skip that for now. But notice that, you may have your functional specifications you may come up with independently testable features, you may come up with a model or some actual values, and then actual values from the testable features, or maybe you need a model at first to get a better idea. And that's what we're going to talk about this side. Beforehand, we just derived some representative values from it, but now we're going to actually look at a model and see if we can come up with it. So I did talk about this a little. They're used in specification or design and have structure for selecting good classes of behavior. In combinatorial testing, it's difficult to capture the structure clearly and correctly in the constraints. It's also just another way to look at your test cases to hopefully give you more insight to what's going on. So coverage is similar to structural testing but applied to your design model. All right. So let's go ahead and start talking about different ways to come up with model-based testing, and we're going to go into different types of models and how we can derive test cases from them. So the first one we're going to look at is the finite state machine. Very common model. One example is UML state diagrams, but you can have other state diagrams as well. So they actually do put out an informal specification. I believe this is in your book. I'm not going to read this whole thing out right now because it is quite the wall of text, but this is talking about a maintenance function for, let's say you're selling some item and a customer says it's defective and maybe they either want it repaired or replaced. And so this is the specification of how that process occurs when the customer comes back and returns the item or asks for it to be replaced. If you notice, if you look through this just summarily, you have if, and so forth. And then once repaired, the product is returned to the customer. So let's look at one of these ifs. If the product is covered by warranty and maintenance or a maintenance contract, maintenance can be requested either by calling the maintenance toll-free number or through the website, etc., etc. So if these things hold, one of those two things holds, then they can go through and call for a maintenance report. And there's other ones as well if you wish to pause the video and read through them before we continue. But notice I can have multiple choices in the first step. Other things can determine possible next steps and so forth and so on. So it can get somewhat complex. Again, if you look at the state machine, again, sorry, I don't know why it comes out this way. You start at 0, no maintenance. And let's say that they had, for example, right here, it's under warranty. They can either wait for it to be picked up or it gets sent to the repair, or maybe they drop it off at the maintenance station. Over here you may have maintenance with no warranty and they'd have to determine whether to accept it or not, and either accept it or just go ahead and return the item saying sorry, it's not under warranty. And then once it's under the repair station, maybe you can say it's repaired, send it on. Otherwise you may have to send to the main quarters and do main headquarters and do some more repairs and whatnot before you have it repaired and returned back to the customer, which would be the no maintenance situation because you were going to mark it resolved. All right, so this is a common finite state machine. Test cases. Usually you want your test case or a test suite to consist of the transitions. 0 to 2, 2 to 4, back to 1, back to 0. So that was 0 to 2 to 4, back to 1, back to 0. AKA they asked for maintenance and they were trying to decide if we're going to accept it. Nope. And then return it back to the customer. And then, of course, other test cases going through the different situation. The question is, how do we know if the test suite is thorough enough for our model, and how can we judge this? Well, we can usually think of as state coverage, make sure we go to every state, or we can think of it as transition coverage, make sure we visit every edge of the transition. The second one is the most commonly used criterion because we usually are trying to test to make sure you can go from one state to another via every channel or every possible channel. And in a state machine, usually, since there's no extra memory, that's actually pretty thorough because you're then testing every possible transition. Note that, I remember, a finite state machine doesn't have extra memory on the side. There's no stack or anything. So when you're in one state, that's the state you are. There's no like substates inside of it. Let's see, past sensitive criteria. Well, like I said earlier, this really all comes down to, this should have no distinction based on how we reached a state. This should be true of a well-designed state machine model. Again, you don't have memory, so getting to how you get to the state actually does not matter, or it should not matter. But if for some reason it does, there's a couple other coverages that you can look at if you really want to. But really, if you can get to a state and that actually matters how you get there, you need to redefine your finite state machine or come up with a different model that uses memory. All right. Okay, so we talked about the finite state machine as a model. We're going to also talk about design tables, decision trees, or flow graphs. And we're going to look at this in the next one. But before we need to also go into another example of a specification. This presentation is going to have a lot of different examples here, so we got to kind of refresh our memory or start over every time. So this is a new specification. This one has to do with looking up how to calculate the price for a good for someone. So, for example, institutes like educational institutes may get a discount, or maybe someone has found a special discount code on the internet that they wish to try and apply to a product. So this is going to be the specification of how we go about testing the mechanism to determine the final price. Yeah, so do notice that educational prices charged based on the educational account in good standing. No further discounts apply. Special price non-discountable offers, sometimes complete configuration offered at special non-discountable price. When a special price is available for configuration, the adjusted price is the non-discounted price, etc., etc. Or whichever is less. So when you have a special price or multiple discounts, you just figure out the one that's less and then you take that. All right, so you might have a decision tree. You can here notice that we might have an education account and an individual account. Over here, we did not talk about a business account. We're leaving that out for now. But notice that if it's an education account, you need true on these two, obviously. And then maybe depending if they're, I don't remember what SP or SC stood for. There might be different sub types of education. And then individuals as well, again, not an education, not a business, but they might have different combinations inside of them. Now you're going to probably want to have some constraints. aka you can either be an education account or a business account. That's very common when you're going out there. So that can help with simplifying your test cases, because then you're not going to have true here and true with business accounts. It's either one or the other. That helps simplify this table a lot. And maybe at most some other types of properties as well to hopefully simplify it as well. And these are probably different types of discounts that they may wish down here. So then how do you actually come up with a condition? You can come up with basic condition coverage that we talked about earlier. You can go into compound condition adequacy, which we talked about again, which is very thorough. And then you can apply modified condition decision adequacy in order to simplify the number of test cases you need. Let's see if they give us a good example. Great. So notice here, 2 education accounts, and basically looks like a special individual account. Oh no, they have a business account over here. to determine that as well. So depending on the actual code or in the slide, we weren't able to go through every single bit of detail here. This may be an example of MCDC. MCDC was talked about a previous chapter, so if you're not familiar with it, please go back. But this is just an example to show you that you can take your model and come up with at least a table. Okay. So we have table-based, we have from a finite state machine coming up with the paths, the edges of the test cases. Now we're going to look at a flow graph-based testing, which is going to look, you're going to think it's similar to a finite state machine, but usually with a flow graph, there can be different substates, so to speak, and a lot more logic. So the example for the flow graph is maybe processing a shipping order. Customer has decided to purchase an item, and towards the end of checkout they need to have the item shipped to them. So you need to come up with a system of how they're going to ship it. Are they going to first off, if it doesn't cost a lot, maybe you're not going to allow them to ship it, or you'd have to charge something extra. You need to make sure their shipping address includes everything, aka it's valid, and then find out what their preferred shipping method is. If it's domestic, they can go by land, freight, expedited land, or overnight air. If it's international, they can only do either air freight or expedited air freight. Shipping cost is calculated based on address and type of customer, aka individual, business, or educational. Individuals can use a credit card. Business and educationals can choose between credit card and an invoice. The card information, you must have valid card information, essentially. The outputs of the process ship orders are so it needs to, when it's done, it's either valid, saying that the output indicates can be processed, or it's not valid. The total charge tells you what the charge is, and this number is only important if it's valid, of course. And then the payment status, if all data is processed correctly, then go ahead and say true, otherwise it's false. So notice you have three outputs. Is it valid? What's total cost? And did the payment actually get processed? You might look at a flow graph like this. I'm not going to go through each one of it, but notice that this is a little different than a finite state machine, because when you go and you're trying to, let's see, where's the calculate total charge goods, but calculate domestic shipping, that's going to be based on the shipping address, which may change from instance to instance. So it's a little different. You're still going to have basic test cases similar to beforehand. Excuse me. But in general, you'll probably want to be looking at simpler techniques. For example, here you have branch testing, making sure that each branch is done. But you could also go back and do conditional testing in MCDC as well. All right, lastly, we're going to go through grammar-based testing. If you have not taken a compilers course or an algorithms course that covered grammars, this may be a lot of new material for you. I will try and simplify this. Note that for this course, we're not going to be focusing on grammar-based testing so much. So you may wish to just try and muddle through this part if you haven't seen it before. But do keep in mind that in other courses, you may need to really do some research on grammar base, or what grammars are, languages and grammars. So do keep that in mind, that if this is very new to you, you may want to start researching a little on the side. But this is for very complex inputs that can be described by a context-free grammar, which is a very common parser or grammar used to parse most of our programming languages, C, and so forth and so on. Grammar is very good at representing inputs of varying and unbounded size. Notes beforehand, we'd have one shipping address, one type of credit card information, etc., etc. But maybe you might have different types of computers that can hold different numbers of slots, or maybe they can order a whole slew of different number of computers, and they can all be of varying specifications. So the grammar is very good for parsing and making sure that all that's put out correctly. Here's some more examples. Complex textual inputs. Okay, that's a little generic. Trees, search trees, sparse trees, very good. For example, XML is a good one, or HTML. Program structures, which are essentially very complex textual inputs. So test cases are usually strings generated from your grammar. Coverage is either the production coverage or a boundary condition, annotated each recursive production and minimum maximum number of applicates, then generate the next one as well. All right. So here's an informal specification, aka here's our example. You might have a check configuration for when they're ordering to check the validity of a computer configuration that someone's ordering. So you must have a model and then a set of components. So a model identifies the product, determinant, etc. The model number will say what the rest of it can have. So once they select a model, they will then be given an opportunity to put in a certain number of slots or different other characteristics, CD, DVD writer, etc., etc. Then of course you may have a set of components that go in different slots. Great example here is default configuration for Chipmunk C20 includes 20 gigabyte hard drive, 30 or 40 may also be selected, and different type of operating systems. This is the grammar. The model is usually of a model number, or followed then by sequences of component sequences, and then of course optional sequences going on. You notice down here a model number is a string, as well as component type, component value, and etc., etc. So this is a nice simple grammar. You can also add some limits to it. Maybe you can only have 0 to 16 components, or 0 to 16 optional components as well, etc., etc. So you might create some test cases. Model 000 might covers the model and then add some additional options to it. So in this case, your test cases are really going to be a lot more verbose and well, maybe not so much verbose, but they're going to each contain a lot of data to actually test a lot of different aspects of it. Now, hopefully you can see that grammars can get very complex because of the total number of different combinations that could possibly occur. But we did talk about actually this example with the Chipmunk a couple of chapters ago. All right, so we got grammar versus combinatorial. So combinatorial is good for most independent parameters. Yeah, we most often factor and flatten. AKA, you want to test very simple or very pointed pieces of it, which is a very good thing to test, and that's what combinatorial testing is. Grammar is going to describe more of a coming up the chain, not so much. I mean, it's still a unit test, so to speak, but it's more a higher level, getting close to a subsystem test or an integration test, because now you're starting to integrate multiple components or multiple unit tests together. And that's what grammar-based testing is actually very good for. Okay, so quick summary. Hopefully most of that made sense. But models are very useful abstractions. Again, a model is an abstract concept to try and give us some useful feedback on what we're trying to do. They're very useful in specification design to help us think of and communicate complex artifacts by only emphasizing the key features, and then of course suppressing the details, ignoring the small things that aren't going to matter right now. Well, hopefully don't matter, I should say. They also help with conveying structure. You can use them in systematic testing. Notice, like I was saying, that you can use the grammar for integration tests. To some extent, you can start working on system tests as well with this, if you can actually push it all together, which would be great. Common model-based testing techniques are based on state machines, decision trees, and of course grammars, but we can apply the same approach to other models as well. All right, so that's it for this chapter. Sorry I've been a little late on homework. I'll try and catch back up, but go ahead and get started on this chapter's homework.